How are you doing in the project? Okay. So when you start to work on the practical part in the lab, you just tell me about the day that you're going to work in the lab. Maybe I will dedicate one day when you are ready. So you'll be in the lab and I can I'll be in the office so I can help you. Like you can choose any Tuesday or Thursday, and then I'll give you this day free and I'll be staying in my office in the lab. And if you have any question, I can help you in the practical part. And I hope that I can do 2 tests because we finished test 1, finish the midterm. So I'm hoping that we can do 2 tests because the times like we have 1 month, right? And then we have the Thanksgiving, then you come back maybe for 1 week, right? And then you'll have the final. So I wonder how can we do that, because I want to do like 2 tests. And so you'll be done with the 3 tests. Then I will choose like the best 2 out of 3 to put in your grades. So maybe I will accelerate test 2 a little bit so I can have time. We have enough time for test 3. So maybe you can say after 2 weeks, we'll have test 2. And then when you come back, we'll have like test 3 that will be before the final by 1 week, like be like a revision. Of course, will be only on the last topics, but just be like helping you to revise before you finish the final. Thank you. Okay, so that's not my turn. So my turn. So we are done with series, parallel resistors, and everything. We're done with the resistors, and it's you can review these topics before the test number 2. We what's left in the syllabus this semester: capacitor, inductor, and introduction to AC. Just maybe it will be like 1 lecture or 2 lectures on AC. So till Thanksgiving, we'll be working with capacitor and inductor. And we have enough time, because we can say we have 4 weeks to finish capacitor and inductors only. We have enough time. So feel free if you because this topic is maybe it's kind of new to you. I know that you studied capacitor before, but we are dealing with capacitor from electric engineering point of view. So I will revise maybe the first 10 minutes about the physics of capacitor, but then after that we'll see the application of capacitor itself. Is it important? Yes, capacitor and inductors are very important. So let's start capacitor. I'm sure that you studied that in physics. So what's capacitor? Anybody know what's capacitor mean? Yes.
So it kind of acts like a battery, like a voltage source. So it has like 2 plates and then like some type of material in between.
Yeah, it's 2 plates, and these 2 plates made from conductive material or non-conductive material? Conductive material. So you have 2 plates made of conductive material, and between these 2 plates, you have insulator, or the material it does not conduct electricity. And usually we call it, there's a very specific common name for this insulation between the 2 plates. Do you know the name? There is a name for it. As engineer, we deal with it. We call it dielectric. Dielectric, okay? So this material that you see in green here in the picture, we call it dielectric. It means insulation material, like mica or something like that. Of course, the objective of the capacitor, as you said, it's store electric charge, store energy. So the main difference between the capacitor and resistor, at resistors, they are consuming energy elements. They consume energy. The proof for that, when electric current flows in any resistor, it produces heat. You will see it's getting hot. It means that the electric energy is consumed in a form of heat. But capacitor and inductors, both, we consider them not consuming energy material. No, They are stored energy material. They store energy inside. So the capacitor stores the electric energy in a form of electrical or electric field. Because as you know from physics, I'm sure you studied that, if you have two plates and of course that's connected to a battery, positive and negative, so the positive charge will be accumulating on the one plate and the negative charge in other plate. There is a misconception about the capacitor. When we draw electric circuit, we think that that the electric current go like that. Never. In resistance, it's true. If you connect it to a battery, the electric current go through the resistance, go to the end. In capacitor, it doesn't go through the capacitor. It doesn't. Why? Why do you think that the electric current here, that's wrong. It doesn't go through the capacitor.
Wait, are we talking about DC?
Because what?
DC?
In DC or AC, capacitor, by the structure itself, we said that it's two plates and insulation between the two plates, or the electric material, this insulator does not allow, shouldn't. So if the electric current go through this insulator, it will break down the insulator and is not capacitor anymore. It would be like a wire. So the electrons would be going, going and coming like that. That considered to be that there is flow of electrons, but doesn't have to penetrate through the two capacitors. If it did happen, you will see spark, explosion. It means that the electric material has been broken, not working anymore. All right. So because some they still till now, even they graduate, and they took some of them, and they think the electric current goes through the capacitor, doesn't go through the capacitor, or the capacitor will not be a capacitor anymore. And there are many types of capacitor, as you see here. The one that maybe you can see in the lab, this semester, this capacitor that it's a cylindrical, they call it polarized electrolytic capacitor. It means has polarities, has positive and negative, and has voltage rating written on it. Usually, always, you will find, for example, 12 volts, 9 volt. What does it mean? It means when you are dealing with this capacitor, you got to be sure that you connect the positive polarity of the capacitor to the positive voltage, the positive potential, and you connect the negative polarity of the capacitor to the negative potential, negative voltage. If you flip them, it will explode. And there are big capacitors. I have one student one time in the lab, and he was working with huge capacitor. We call it super capacitor, and you can see it in the videos, like a cylinder like this size. This is like a palm. He was about to lose his eye because it has chemical inside of the cylinder. Why? Because you flip the polarity and connect the positive to the negative, negative to the positive. That's wrong. That's number one. When you are working with capacitor in lab, should be especially this type. There's other type that it doesn't matter. That you work with AC, we call it ceramic capacitor. It looks like a disc and has two pins or two terminals. That's okay. They are designed to work with any polarity. But this one designed to only work with the right polarity, the minus and the plus, as you see. Number two, the voltage. If the voltage rating on the capacitor 12 voltage, you should not use it with any voltage more than 12 volts. Actually, as precaution, we use it with less a little bit. But you can use up to 12 if it's rated 12. 9, maximum 9 volt. What happens if you have extra voltage? It will explode again. It has chemical inside. That's very dangerous. So you be careful and cautious when you're working with polarized capacitor. And that's the way. I'm sure that you saw this capacitor before. They are everywhere, even because you use it in power supply. If you have power supply, if you had the chance one time to open power supply or any board, you will find these capacitors there. And usually they are used with power supply to regulate the voltage, to make it like constant. I'm going to talk about. They are used to regulate the voltage. Like if you have ripple in the voltage, then it will make it smooth, like straight line. And that's how it operates. Okay. Of course, there are charges accumulated on both, and the quantity of the charge we call it Q, and it's measured in Coulomb. That's the charge, and we studied that when we explained the electric current. So Q, the charge, and we know that the unit of the charge is the electron. So you can have 1,000 electron, you multiply the 1,000 by that one charge of electron, you can get the Q, capital Q, the total amount of charge. So every capacitor has a capacity that, or a certain amount of charge that it can store, not more than this. This is like, imagine like if a tank of water has a capacity, like say 2 liter, 1 liter, then that's the max. You cannot, it will spill out. The same thing capacitor. It store charge. It can the charge can be accumulated in these plates, but it's limited. You cannot just charge to infinity. So we call it the capacitance. C is the capacitance. So every capacitor has a parameter called capacitance and measured in farad, like resistance measured in ohm. The capacitance of the capacitor measured in farad. How you calculate the capacitance of a capacitor? You divide the Q, the charge, by the voltage applied to it, because as you see, that's the voltage here applied to the capacitor, and this has a capacitance C. So you can tell how much charge this capacitor can store on its plates. Definite amount. So C is the capacitance in farad, and of course, usually you'll find that the value of the capacitance of any capacitor is not big. You will not find, for example, 10 farad, 100 farad. No. You'll find like microfarad, picofarad, like 10 power minus -6, and things like that. Of course, super capacitor, they can handle, they have bigger capacitance, but it will never reach like 100 farad or 1,000. No. Still, maybe to reach millifarad maximum. That's a big one. And use supercapacitor to store energy, especially when they are used with the renewable energy. Because as you know, renewable energy, it's like if you have a solar energy, you have the PV panels, then it produces DC voltage. And there are batteries there. You store the energy in it. So 1 farad, which is the unit of that, it's equal to, if you look at this equation, so C be 1 farad is equal to 1 coulomb is the charge divided by 1 volt. That's the meaning of 1 farad. What does it mean? And that's I will upload this file. It tell you about the farad, the microfarad, how you convert from farad to microfarad, from farads to picofarad, farad. So you can have it and use it when you are solving the questions till you get used to it. And most of the time you'll find they are using microfarad. Okay, and here you have the microfarad. That's like 10 power -6 of the farad. So let's start solving some question here about the unit. So you have a capacitor, store 50 microcoulomb. All right, that's mean that's Q, right? So you have Q equal to 50 microcoulomb with 10 voltage across its plate. So you have a capacitor like that, and then you are connect a voltage battery, which is equal to 10 voltage, and the Q is equal 50 microcoulomb. So what is the capacitance? The capacitance of this capacitor in microfarad. So, well, we know, I always write this one. I say Q is equal CV. The total charge equal the capacitance times the voltage across the capacitor. So you have 50 microcoulomb, which is it means 10 negative 6 equal C that I want to know, and the voltage is equal 10 voltage. So C will be equal 50 times 10 negative 6 divided by 10. That will give you infrared. That will give you infrared. If you want to get it in microfarad, so multiply it by 10 power 6. So you can get it in microfarad. So 10 power 6 will cancel 10 negative 6. So, and 50 over 10 will be equal 5. So the answer is 5 microfarad. Simple. So that's the capacitor. When you look at the structure of a capacitor, we said 2 plates and you have insulator between the 2 plates. To design a capacitor, like if you remember the resistance, you can find the value of the resistance if you know the dimension and the material of the resistance. Let me refresh your memory. If you have a resistance made of conductive material, of course, R, and you can say that the resistance is equal, it is proportional to the length of the resistance divided by the area, because it's proportional inversely with the area, and then it depends on the material, so you have the resistivity. That's the format for how to find the resistance using the dimension and the material itself. We did that before on resistance. What about capacitor? If you have a capacitor, the capacitor we said made of 2 plates. So if we do 2 plates, and you got the material, insulator material between. So to calculate the value of the capacitance of this one, depending on the dimension. So we said capacitance is like the ability of a capacitor to store energy. So how can, what the parameter, if we talk about the area of the plates, what do you think the capacitance will increase with the area or decrease with the area? If you have capacitor with bigger plates, do you think it will store more charge, a lot of charge, or yes? So proportion directly with it. And if the distance or the space between the 2 plates, let's call it D, the distance D, it's proportion inversely with it. So every time D is small, it can store more. And of course, on the material, we call it epsilon. So that's the capacitance. And it depends on the area of the plates, proportion inversely with the distance between, this separated distance between the 2 plates. And epsilon, we call it permittivity. It's epsilon. Okay. Let me just.
Area of both of the series?
No, one plate, because they are parallel. They are equal. The area of one plate. That's a good one. Let me just make it clear here. That's the area. One plate. And epsilon, we call it permittivity. And let's talk about the epsilon, the permittivity. Of course, when the permittivity is higher, the capacity to store more energy will be higher, and this constant, it depends on the material, of the dielectric, the material of insulator. And if you have only air, you can have air. Air is like insulating material. So epsilon in this case will be epsilon naught. That's the permittivity of the air. Or we can say that that's absolute permittivity. It's a constant. I'll give you the value of it now. Absolute permittivity. If you have another material, it will be different than epsilon naught. And always there is a relationship between any material and the vacuum here. So in general, E is equal epsilon naught, epsilon R. You did that in physics. Epsilon naught, we said that the absolute permittivity. What about ER? ER is the relative permittivity. And there will be a table that it will show you the value of the relative permittivity to most common material.
Professor?
Yes.
So epsilon naught is the permittivity in a vacuum, or is it the permittivity of air?
Vacuum.
Okay, thank you.
You're very welcome. Thank you for your question. Vacuum. And it has a constant value. Let me give it to you. Epsilon naught, the vacuum, 5 times 10 negative 12 farad per meter. I wonder if I have table. It shows, yeah, I have table here. And let me show you the table here. This table shows the relative material. And for just the one ask me about it's vacuum or air, we don't distinguish air or vacuum. It means we don't put anything between the two plates. So of course you'll find that the relative material is equal 1, because it means epsilon is equal epsilon naught. ER will be equal 1 in this case. So in this case, ER is equal 1. And you have like paper, for example, it's 2.5. ER is, that's the value of ER, 2.5. So if you want to find epsilon, you have to multiply epsilon naught times epsilon R. And ER, epsilon R now, it's equal 2.5. And epsilon naught will just give you the value. This is the epsilon naught, 8.85 times 10 power negative 12. So this table, it will show to you, look at the ceramic here. The ceramic is 1200. 1200, that's a big relative material. So you multiply it by epsilon naught, you get a big, that's maybe the biggest value here we can see. So what does it mean? It means that E for ceramic is really high. And since it's high, what does it mean? Epsilon is high, and we know this is a format, so epsilon, this is high, so it means it can store more charge. If C is high, it means the capacitance is high, it means you can store more charge. Okay. Let's take an example for how to calculate the capacity. Let's say that we have two parallel plates of capacitor, and the area was given of the capacitor 0.01 meter square, and the plate separation. When you say plate separation, means D. The two plates are separated by this distance 1 mil. Of course, you are familiar with mil. We did that in wire gauge system. But in any way, 1 mil, let me give you the equivalent of 1 mil. If you see 1 mil, you can just write it 2.54 times 10 power negative 5 meter when you convert it to meter, because the area was given meter square. Because to change or to convert from the bridge system to SI system, you know that 1 inch is equal 2.54 centimeter. So if you convert 1 mil, you will find it's equal 2.54 times 10⁻5 meter. That's given. You don't have to worry about it. And the dielectric is mica. That's the dielectric. So they want to calculate the C. What is the capacitance of this capacitor? So got to go and look for the table for the mica to find ER. So for mica, when you look at the table, you find it's epsilon R, the relative permittivity is equal 5. Once you found the relative permittivity, go ahead and calculate the permittivity for the whole thing. That will be epsilon naught times epsilon R, and epsilon naught we said before is equal 8.85. You don't have to memorize, of course, this number. I never memorize. Times 10 negative 12, and ER is equal 5. You get the value for E, and you know that the capacitance, it can be calculated by epsilon times the area divided by the separation or the distance D between the two plates. Then you substitute 8.85 times 10 negative 12 times 5. That's the epsilon, and the area is given 0.01 meter square. That's important that you be everything in meter here. It's given, divided by the distance. It's already given, converted to 0.4 times 10 negative 5 meter. Make sure that you are using the right unit. Then it will be a small number, so you got to convert it to microfarad. So always you do that, multiply it by 10 power 6 to get the result in microfarad. So the result will be 0.017 microfarad. Even you have microfarad, still small and very normal. You can see this value in capacitors written 0.1 microfarad and so on. 0.22 microfarad. There are common values for the capacitors. So that was a direct application of the formula that we just learned. All this, I supposedly that you did that in physics, but I said, okay, I'll go ahead and review it. So I think we review here, we reviewed the physics. Now let's go ahead and start the engineering business. Okay, we know about the capacitance, we know about the effect of the dimension in it, and the relationship between the charge and the capacitance and voltage. Now we want to use it. And I will explain it more than the textbook, because in textbook they are brief a little bit on it. I want to make it in detail. The most important thing in any element that you use, especially passive elements, that you know how to get the relationship between the voltage and the current. In resistance, I always like to mention what we did learn before. In resistance, we learn if you have voltage apply to a resistance, you have voltage across the resistance, and current will go on the circuit. We call it IR. We know how to do that using Ohm's law. So we'll say that the voltage across the resistance is equal the resistance itself times IR. What does it mean? It means if you have if you want to get the relationship between the voltage and the current across the resistance, so it means that the current is equal V over R. So it will be like you can write it 1 over R times V. So 1 over R is a constant number. If you have R, for example, 10 ohm, so 1 over R will be 0.1. So it means I equal 0.1 V. So it's a straight line, start from 0. So you can just go ahead and make a straight line to show the relationship between the voltage and the current. And the slope is equal to 1 over R. If you flip the diagram, you make V y-axis, x-axis, you will have V equal Ri, so V equal R. But I'd like them to write it I. What about capacitor? Capacitor is completely different than this one. If we have a capacitor and we connect it to voltage source, you have here the voltage, and I will do that in a small letter like that, the lowercase one, and I will write it function of time. Said, can you do that with the resistor? Yes, you can do that with the resistor. Just because we have DC, we use the letter, capital letter or the uppercase letter. But of course, you can do that. You can say that the voltage across the resistance is equal R times I, function of time. We'll learn that in AC. It's fine. And this is special case. But for the capacitor here, let's just start with the lowercase letter. So that's the voltage, and the current, we call it I of T. So what is the relationship between the voltage and the current? Great. Let's start from scratch. What is the definition of current? If you remember, we did that in the first chapter, in the first few lectures, maybe the second lecture this semester. The current. What is the current? Definition of current. Yes, that's right. Rate of change of charge. 1 amp means 1 coulomb in 1 second. So if you want, what does it mean 10 amp? It means you have 10 coulomb in 1 second. So the current is the rate of change of charge. Rate of change of charge. So that's the definition we learned before. I is equal rate of change of charge. Even I'm going to use Q small because I'm working now in time variable. That's the definition of, I will drop the T, the independent variable, so make it easy. So let me just write I, but it's all function of time. I is equal dQ by dt. Okay, for capacitor, what's the relationship between Q and V? We know the relationship in capacitor, Q is equal CV, right? So now I'm going to do, I say D by dt, and then I replace Q. Q is the charge. Let me just remind you, because I'm using small letter here. So it equals CV. That's the charge. In our case, we are considering C is constant. Do we have variable C? Yes, you can have variable C, but now I'm working with the basic capacitor. So C is constant. I get it out of the differentiation. So I can say that C times dV by dt. That's the relationship between the current and voltage across the capacitor. I is equal C dV by dt. What does it mean? The current in a capacitor depends on the rate of change of the voltage. Rate of change of the voltage. So if you, let me just write now, I in capacitor is equal C dV by dt. Not any voltage, not any current. Current, that's the capacitor current V across the capacitor. What does it mean? It means current is proportional directly to the rate of change of the voltage. Let's take a special case. What about if the voltage DC? The voltage DC. Let's say that the voltage, if the voltage is equal DC voltage, I make it capital now, it means constant. 10 volt, 12 volt, 13 volt. So what is dV by dt? 0. So if it's 0, the current in the capacitor will equal 0. So we can say if you apply DC to the capacitor, it will operate as an open circuit. Because what does it mean current equals 0? No current. Means like a wire, cut a wire. So we can now say a very important result, that capacitor acts as an open circuit. Open circuit, okay? When DC voltage is applied across C to be like an open circuit. Remember from this relation, I is equal C dV by dt. If you want to sketch a relationship between the current and the voltage, like in the capacitor, I mean, like in resistor, now you will have I, but not with V, dV by dt. And you'll find that it has slope equal C, because you know that I is equal C dV by dt. It's proportional not to the voltage, to the rate of change of voltage. What does it mean? Every time the voltage is changing quickly with the time, then you will have current. The voltage not changing with time, like in DC, current will be 0. And this is the case. When dV equals 0, that's as DC. Then when you start changing the voltage with the current, then you start finding the current. So how you find the voltage across the capacitor? Well, I'm going to use the same relationship. If you have I of t, it's like we're reviewing calculus with you here, but in application, C dV by dt. Before I find the voltage, let me just have an application. What about, let me give you an example before I start to find other things, how to calculate the current. Let's say that the voltage look like that. You apply voltage to the capacitor, and let's say it look like let me make it exponential to make it easy for you. Let's say that the voltage was equal 10 E minus 0.2 T when T greater than 0. So I will say something like that. That's the exponential function, decay exponential function. So what the current look like if you apply this to the capacitor? You will have I of t equal C, and let's say that the C is equal, let's say equal to 20 microfarad. I'm taking a big value a little bit. 20 is a big one. Okay. So let's say I is equal C dV by dt. I know the voltage now, so I find first dV by dt. What is dV by dt? We want to differentiate this one. So we have 10 as a constant, and then the differentiation of the exponential function will be the same, will be e power minus 0.2 t times the differentiation of the exponent itself will be minus 0.2. If you don't understand how to differentiate, I can do it again. The 10 is constant outside differentiation, and then I differentiate the exponential. It will be the same. I just write again, as you know, and then I differentiate the exponent, the minus 0.2 t, because it's function of time. So it will be minus 0.2. When you differentiate minus 0.2 times t, it will be minus 0.2. And then I simplify the result. It will be negative, and 0.2 times 10 will be 2, e minus 0.2 t. That's dV by dt. Now I want to find the current. So the current in the capacitor will be equal C. I multiply this by C. What is the value of C? 20 microfarad. So I say 20 times 10 negative 6 times negative 2. That's C. That's E minus 0.2 T. So when you do that, you have minus 40 E times 10 negative 6 times E minus 0.2 T. And if you simplify it, it's already simplified, but the result will be minus 40 times 10 negative 6 E minus 0.2 T M. Let's express it in microamp. So you will multiply by 10 power 6. So you have minus 40 E minus 0.2 T That's the current. And the unit is microamp. How you sketch this one? Well, we can sketch this one. You have, that's the voltage. And the voltage, of course, how I sketched like it, because I know it's 10e minus 0.2. So when t equals 0, e power 0 equal 1 times 10 is 10. So I'll start it from 10. And then when t go to infinity, it will be 0. So it will be decaying to 0. So that's the voltage was that was given. The current, I have here the current. Let's just sketch the current with the time, of course. So this equation minus 40. Oh, let me modify this one because it'll be like the current will be negative, right? So I'll make it like that. The time, and this is the current. So substitute here by when t is equal 0 in this equation. So you have the current at 0 minus 40, and then e power 0 is 1. So be starting from minus 40. So it'll be minus 40. And when you put t equal infinity, so I infinity, e power minus infinity is 0. 0 times anything is equal 0. So it will be like that. So that will be the curve of the current. Okay. Now let's find something about the voltage. How you find the voltage? So know how to find the current if the voltage is given. What about finding the voltage if the current is given? So let me start with the equation I of t is equal C dV of t by dt. I want to find the voltage. So I'll say dV by dt will be equal 1 over C I of t. That's the, I want to find the voltage. So I multiply both equation by dt. So I have dV equal 1 over C IT dt. So I have dV. How I find the voltage? If dV is known, I integrate both sides. When you integrate from 0 to t, from 0 to t. All right. What is the integration of dV? When you integrate any dV, the integration cancel the d, so you get v, and then substitute. You have v of t minus v when it's 0. Because when you integrate dv of t, you get v of t, and then you put the limit from t to 0. So you substitute 1 time t, 1 time 0, the difference equal 1 over c. The integration of it, that will be the integration of it. It depends on the waveform of it. It could be exponential, sine, whatever. All right. So now the expression will say v of t is equal 1 over c. You integrate the current, and then you add the initial one of the voltage. That will be the expression how to find the voltage. So you integrate the current and you add the initial condition. When you do that, it means that the voltage waveform always continuous. Always continuous. What does it mean? It means that the voltage across the capacitor cannot change suddenly, or abruptly. It can change suddenly, just jump from one value to value. What does it mean? It means if you have something like that, and you have two form, and then you tell me which one possible, which one not possible to be the voltage across the capacitor. From this equation, there is continuity of the voltage across the capacitor. So maybe you will find, if you have something like that, or you have something like that, which one is possible, which one is not possible. which voltage waveform I say it's correct and the other one is not correct. Yes. The first one is correct because when you look here, there is continuity. It's like, I mean, if you go and make any line, you will find that to the right and to the left, you have two difference of value of the voltage, not the same one. But here in this one that has square wave, if you draw any vertical line at some places, not everything, just enough one place. Look, for example, this place, at this vertical line, at specific time t, you'll find two values. So it means that the voltage across the capacitor jump from one value to another. It means that the voltage, it changed from one value, even if it changed by 10%, but changed in 0 seconds. That's impossible. Why? Let me show you the equation. The equation of I of t equals C dV by dt. Let me make it simple. So I is equal C dV by dt. The change of voltage with respect to, if the voltage here, it changed from one value to another in t equals 0. Let's say this value was, for example, 1, and this value is equal even 3, small value. So you have C times 3 minus 1, and the same time, t, let's say t is equal, for example, 0.5 second. So 0.5 minus 0.5, that will be equal 0. Anything over 0 equal what? Infinity, right? Can't have infinity current to the capacitor. So that's impossible. But this one, if you draw a line, you'll find that no, there is no two values. It's continuous. That's what I'm saying. It's very important to know that the capacitor can, the voltage in the across the capacitor cannot change arbitrarily. So let me just write, or suddenly not change. So that's very important to know about the capacitor. So we'll say the voltage across the capacitor, any capacitor, can not change That's important. All right. So now we learn how to find the current and how to find the voltage. Okay. I wonder if I have any example for you here. Yes, I give you example how to find the current, but I didn't show you example how to find the voltage. I'll take something similar here. Let's say how to find the voltage. In this example, let's say that we have a capacitor has a capacitance of 2 microfarad. It's given that the current in the capacitor is equal to 6 times E to the power of minus 300 T, 3000. Let's make it big number in 3000 T, and let's say this is milliamp. The question is, and also let's say that we have to give initial condition for the, also you have to, why? Because when we did the integration, this is the, we have the integration of the current, then multiplied over 1 over C, and then you add the initial condition, that's V of 0. Let me just make it clear here. That's V of 0 that we got it from here, you know, the initial condition. What's the mean initial condition? Means that the capacitor, maybe it has charge before the current go there. They have initial charge. Maybe it was not uncharged, would be V of 0 equals 0. Okay, so that's the general form. So let's say that the initial condition or initial charge was 0 voltage. So calculate the voltage at t equal 2 seconds. We need to know the voltage after 2 seconds in this capacitor. So you have a capacitor was not charged, and I connected to some voltage, And this voltage source, it's look also exponential, like the example here. There's the voltage and the current through the capacitor here. I know the. I'm sorry. That was a current source. I'm sorry. That was a current source. That's a current source. And this current source was given as exponential. And I want to know the voltage across the capacitor after 2 seconds. All right. Solve this one. We'll say that the equation that we got, we say that the voltage at any time t is equal 1 over c times the integration of the current with respect to t from 0 to t plus the initial condition that was in the capacitor. In this case, it was given that the initial condition was 0. So I have to integrate. Well, let's integrate this one. Will be equal to 1 over c. C is given 2 microfarads, so I have 2 times 10 negative 6. The integration from 0 to t, the I of t, which is equal 6e minus 300 t dt. That's the equation of the current. So once you write this is the correct formula. Then what's left is just to review your math that you did in calculus. Let's just do it in a fast way. So you have 1 over 2. It's a constant. You don't have to do anything with it. 6 is constant here. So just go ahead, take it outside the integration. Make it simple. And then now we are integrating e power minus 300t. We know that to integrate, let me just do it here on the side. If you want to integrate minus at dt, that's equal to what? The same thing divided by the derivative of the power, which is minus a. That's what you did in calculus before the form, right? So that's what I'm going to do. The integration of e. So now your a is equal to 300. So according to this formula, you will have e minus 300t, the same thing, and then you divide it by minus 300. And the limit from 0 to t. All right. So let's find the result here. So you have 6 here, 2 times 10 negative 6 times 300. How we deal with the negative here on the bottom? So you write it the same thing here, e minus 300t. Because I took only 300 and I put it there, but I left the negative. It's very easy. I used when I was going to do that just to change the limit. When you substitute from 0t to the 0, that will make up for it. That will be a constant number. If let me just simplify for you. At 6 over 2. 6 over 2 is equal 3. This cancels. That will be 2 over 1, 2 over 3. 3 cancel. So you have 100, then 10 negative 6 will be 10 negative, pardon me? Okay, will be 10 power 4. And then you have e minus, you substitute by 0 first, e minus 0 minus e minus t. Yes.
Professor?
When you get the derivative, you're supposed to add exponent to 300 on the bottom and on the top.
It's when you integrate, will be on the bottom. When you differentiate, will be just next to it. Like yeah, like when I did, you see here. Remember when I did the differentiation? You see, I multiplied by negative by 0.2 the differentiation of it. But when you integrate, will be let me write the formula again. When you want to integrate e minus ax at, I'm sorry. If you integrate e minus at dt, that's equal e minus at divided by minus a.
Okay.
But if you are differentiating, will be e minus at multiplied by minus a. That's differentiation.
Okay.
So, oh, no problem. So now I have this
Professor?
form. Yes.
Why did we flip the 0 and T?
Because
was
I have, because I will tell you why. Because I have, if you look at the equation, you have negative sign here. So I want to remove the negative sign, you can exchange this one. Or you want to keep it, you keep T and 0 in the place.
Okay, thank you.
You're very well. That's a good question. So that you have 10 power 4 and E power 0 is equal 1, E minus 300T. So that will be the formula for the voltage at any time, anytime. So if you want to find at 2 seconds, what they ask about 2 seconds, okay? So just replace T by 2 seconds. You will have 10 power 4, 1 E minus 300 times 2. You do that and you will, let's see, shift length, negative 600. It was 300 or 1,000. Oh, okay. Why you guys didn't tell me? You just let me go. No, you got to tell me, yeah. Because you know, 0 would make big difference, you know, because it will affect even the value here. See, you have 0 here, you have 0 here, and then you got it there. Then this will be not 10 to the power 4, that will be 10 power 3. Pardon me? Because you have, I simplify 2 by 2, 3, 3 by 3 is 1, and you have 1,000, 10 negative 6. So 10 negative 6, you go up like 6 zeros, right? 1, 2, 3, 4, 5, 6. And you have 1,000 down. So 3, 0, 3, 0, you get 1,000. So you have 1,000 here also.
It was milliamps in the beginning.
It was milliamp. Or I yes, or I leave it millivolt. I will, that's good that you remind me. It's milliamp. Yes. So that's good. If it's milliamp, so I still have millivolt, but I will convert it. Let me fix this formula now. So that will be equal to 10 power 3, 1 E minus 3,000 T, and that's millivolt because I was milliamp. If you want to convert it to volt, so multiply by 10 negative 3, so you have 1 E minus 3,000 T volt. That will be the voltage at any time. And to find at 2 seconds, substitute by 2. Substitute T by 2 will be 6,000. That will give negative 6,000. What is that? That's like a 0 almost. Let me just check again. 6,000. 1, 2, 3. Yeah, 0. So it's like 1 volt. All right. Because it's a big number. 6,000 is a big number. So E minus 6,000 is like E minus F is equal to 0. So 1 volt will be 1 volt. Yeah. So that will be the how to get the voltage. Sometimes it's given as a form, waveform. That's easy. Let me give you one example of a form, a waveform. Let's say that you have like a triangle waveform, for example, something like that. And this is very practical, by the way. In electronic, usually we are using some kind of, oops. And it will continue like that. That's a triangular form. And was given like 0, 4, 8, and then the magnitude was giving like, let's say 20, and that's voltage waveform. and that's current time. And the capacitor was given 20 microfarad. That's an example.
Thank you.
The question is, find the current in the capacitor. Find the current in the capacitor. That's a very simple problem and very practical problem, because you are in electronics, you are dealing with different waveform, square wave, triangular wave, so on, sinusoidal. So first of all, I know that I is equal to C dV by dt. So the first thing I'm going to do, I'm going to find dV by dt first. So in the same page, you just to do dV by dt. What does it mean, dV by dt? Differentiation. All right. What's differentiation of a straight line? Straight line. Our reflection is very simple. Well, for example, if I say y is equal 3x, what is dy by dx? 3, right? Straight line is like constant. So you have here 20, and of course this will be 2 in the middle. That will be 6. So the first one that when you look at it, you have 20, 2. So the slope of this straight line, 20 over 2 is 10. So the slope is 10. So the output when you look at it will be 10. So that will be 10. So let's just, that's 10. That differentiation. What about the other straight line? The straight line, the slope is the same but negative. So it'll be negative 10. So you just make it negative 10. You might ask why you are stopping here, because the straight line stop here. So and this one stop here. What about again this straight line from 4 to 6? Again, from 4 to 6, it's the same slope. It's like 20 over 2 is 10. So you'll be like that. So, and you will have 10. And you can check this with the simulation package microcap. You put this triangular waveform from the function generator, and then you will see that the current across the capacitor will be like a square wave. If you put triangular wave, it will differentiate square wave. But of course, this is the magnitude 10, negative 10, 10, negative 10, and so on. That's dV by dt. Then multiply it by the capacitor. The capacitor is 20 microfarad. So you come here and just you say, okay, when you multiply C, which is 20 microfarad, 10 negative 6 times 10, see what's the value? That will be equal to 100 times 10 negative 6. Let's make it a milliamp multiplied by 10 power 3. So you have 2, and this 2 zeros will be added to the 5 minus, so be like that. So it will be 0.2 milliamp. So you do just another graph, the same thing, and you will have square wave at the same instant. That is, but the value is not 10 and negative 10, of course. You multiply it by C this time. So you'll have 0.2 milliamp, negative 0.2 milliamp. So that will be the current in the capacitor. That's the current in the capacitor. It looks square wave. So you got to know that the capacitor, if you put the voltage, the current will be the differentiation. Then you multiply by a constant, yeah. So if you want to generate waveform from something, you can think about, I want a square wave. Okay, I'll put triangular wave. Then you get the square wave. So that's how you solve problem with the waveform like that. It's easy. All right. There's only one thing left, and then we're not going to be done with the capacitor. Just it's like I'm introducing capacitor to you. But then after that, I'll explain how you charge it, how you discharge. But this is like introduction to the capacitor, to know how you find the current, how you find the voltage. One only thing is left, which is how to calculate the energy stored, how many joules stored, and it'll be done with today, of course. But still have interesting story with the capacitor. Well, what is the definition of the power, the definition of energy that we started this semester with? We always use this letter for energy, like using textbook, and P for power. So don't forget that. Power, you know the power. How you calculate the power? Multiplied voltage by current. You remember in the resistor? Voltage by current. But maybe you are going to say, but we learn also that the power equal R I square V square over R. But I'm not talking about resistance now. So I'm using the general form. General format doesn't depend. It's resistant, capacitor, inductor. It's the voltage times the current. Give you the power, right? So the power is equal V times I. Now I'm dealing with capacitor. So I know from the capacitor that the current is equal C dV by dt. Right? So now the power will be equal V times I, and I is equal C dV by dt. So you have C V dV by dt. That's the power. Well, how do you find the energy? The energy, the difference between the energy and the power, you multiply the power by the time. Like if you have a light bulb, we did that before. If you have light bulb 100 watt, this is the power. The energy, you see how many hours you use it. Use it for 4 hours, 3 hours, and multiply the hour by the power, you get the energy, joule. In general, when you are dealing with the function of time, so the general formula, you're not going to multiply, you're going to integrate with respect to time. So the energy is equal the power, integrate with respect to time. A special case, if everything is constant, you can say the energy is equal power times time. That's a special case when everything is constant. But now we are dealing with something function of time. You integrate. That's the value of calculus. Today, maybe you will see the calculus or the math has application, real application, the meaning of it. So when you multiply, if you have constant number, 4 times 3 is, but something is changing with time, you integrate it. It will be the equivalent to multiplication. And differentiation is like the general for division. So now we are multiplying, but if they are constant, if they are not constant, you integrate. What is the power? Power is equal C V dV by dt. And then you multiply it by dt, multiply it by dt. So what happened? Dt cancel with dt. So what's left? The integration of C V dV. C is constant. So V dV. What is the integration of V with dV? Let me refresh your memory. Remember in the integration x dx. What's x dx? What's the integration of x? Half x squared. You square divide by 2, right? Why? Because x power 1. So you add 1, divide by 1. So it'll be x squared over 2. Right? So I will do the same thing. The integration of V dV. V power 1. So be V squared over 2. So equal half C V2. So the energy stored in the capacitor is equal 1/2 C V squared. That's
And
how
we don't have to put.
Go ahead.
And we don't have to put the 0 to t on the integration.
Well, you do. Yes, you do. In general, no, but not t. I'm sorry. You are integrating with respect to V. So from 0 to V. You are integrating with respect to dV. So from 0, if you are integrating with respect to dt, from 0 to t. But you are integrating from 0 to V because you are integrating with respect to V variable. And of course, when you make 0, I'm considering it was not charged before. So the energy stored would be equal half CV squared. That's a nice form to calculate the energy. I'll just give one example on the energy, and then we'll be done. Let's take just an example we did before. I will take a simple example. Let's have like a DC. You have a capacitor, and the capacitor is equal to 20 microfarad. And you have a DC voltage. You can have DC voltage. This is the general one. You can V. It could be function of time. It's fine. Okay, but I'll give it easier one. And you have 12 voltage. You want to find the energy stored in joule. So we'll say that the energy is equal half. The capacitor is equal 20 microfarad, 10⁻⁶, times V squared, 12 squared. You will have half times 20 times 10⁻⁶ times 144. That will give 144 times 10 divided by 1, 2, 3, 4, 5, 6. So if I multiply by 1,000 to make it milliwatt, so I get, so multiply this by 1,000. You get 1.44 milli, not millijoule, I'm sorry. That's an energy. This is the energy stored. If you put 12 voltage in 20 microfarad. Of course, the energy stored in the capacitor, it depends on the value of the capacitance and the voltage.